Hi, my name is Andrew Daher, and I'll be presenting on the first solution to the lost in space problem. My co-authors are Dr. Scott Palo and Dr. Daniel Kubicek of the University of Colorado Boulder and LAS, respectively. These are the Marco CubeSats. They were small satellites launched in conjunction with the InSight Mars lander in order to be a relay to Earth for the InSight mission. They're 6U CubeSats, and they're the first small satellites to be interplanetary. These two satellites, though, are the perfect examples of satellites that are lost in space. Marco B was lost on December 29th, 2018, and Marco A was lost on January 4th, 2019. When and if these satellites recover from their faulted states, they will not have any information of their time, position, or velocity. The purpose of this research was to devise a way for satellites in this situation to autonomously recover their time, position, velocity with only onboard resources. We hope to develop the architecture to demonstrate the complete autonomous cold start determination of time and state, position and velocity for interplanetary autonomous optical navigation systems. The motivation of this is to reduce mission risk, reduce the cost of faulted recovery systems, advance the time to recovery of satellites, and enable small spacecraft missions for deep space. So there's two meanings when I talk about the lost in space problem. One is the attitude lost in space problem, and this is solved via star trackers and is a well-known problem. The next is the orbit determination lost in space problem. The current furthest solution for this is a closed form solution that only solves for position but negates time. Unfortunately, this doesn't give you a full solution as you need time, position, and velocity in order to do that. So how can a lost in space problem happen? There are a variety of reasons. One could be a processor reboot, either due to a watchdog timer or a power loss. This could cause your satellite to be down for minutes, days, or weeks. The next is a software bug. You could have a problem in your software that does not allow your satellite to write time, position, and velocity correctly. This was evident in the Dawn spacecraft that was launched by JPL. You could have an initialization state like the CubeSats on the EM1 launch that will not give you your time, position, and velocity when launched. These satellites will have sat on the shelf for weeks, months, and then be launched with no a priori information and have to obtain communication relay back to Earth. You could also have a memory corruption caused by a single event upset that corrupts the portion of your memory that saves your state. So you need to either constantly be getting your time, position, and velocity updated, or you need to get it once and resave it to an uncorrupted portion. So to solve this problem, we aim to use optical navigation and find planets and the Jovian moons. Multiple targets increase the data available to create a solution. And when you're within 1 to 10 AU of Jupiter, the Galileans can be used in conjunction with a CubeSat star tracker as their luminosity will be bright enough. And why time, position, and velocity? Just position and velocity gives a relative solution, not an absolute one. With the periodicity of the planets, you can have multiple solutions that exist, and the less planetary objects that you have can increase this periodicity that you might see. So we want to obtain an absolute position in absolute time. Also, communication schedules would be based on time. And so if you only obtained a position and velocity, if you didn't know your time, you wouldn't be able to communicate back with Earth or another satellite relay or anything else that might be only looking for your communication at a specific time. So for a concept of operations, it's fairly straightforward. We want to determine the attitude via star tracker. Then we want to locate the sun direction with a fine sun sensor. And then we want to estimate the sun distance. Now this is done with an irradiance measurement from your solar panels and from your fine sun sensor. This is the worst of the three measurements that we are using and the one that has the greatest source of error. And we'll get into that later. We want to then find the planetary objects by estimating the spacecraft distance from the planets geometrically. And this can allow you to use an advanced search algorithm to limit your space that you have to search with your star tracker. We then want to scan that field that you've just solved for with a star tracker, and then image process. In the event that an advanced algorithm isn't available or it yields too large of a result, you can do an all sky scan and then eliminate the stars that exist and just focus on the planetary bodies. We then want to detect the objects and estimate their location from the ephemeris that we have on board. And then we want to image those planetary systems. We want to do that in a specific and concise way that we will also get into later. From then, you can get an initial estimate of time, position, and velocity. But using just planetary bodies will only give you about an order of magnitude away from your actual answer that you want. You then want to iterate on this continually and start getting closer and closer to that solution space. Given that planets have large periodicities, ultimately you'll only be able to converge on a solution that isn't usable for deep space navigation. So then you want to detect and estimate the location of the Jovian moons. Because they have a finer periodicity, you can then use these to get a fine iteration on your solution. And that'll give you your final estimate of time, position, and velocity. So how we're going to do this is with the multi-mission optical navigation program run out of JPL. This was developed at JPL and used in the optical navigation group. It's been used since Mariner 9 and iterated on for different missions through that. It has three main programs. One is the trajectory geometry program. This is your picture prediction tool. So this is what simulates all the data coming in. Then you have your optical observables and partials generator. This analyzes observations before the filtering process and gets your partial derivatives. And then you have the optical data analysis program, and this is your filtering tool where it runs your Kalman and your batch filters. Now, the algorithm that we're using for this is the algorithm that's used by the picture sequence tool in order to predict where the planets will be based on the ephemeris data in relationship to the satellite. Now, this is done in pixel and line space and uses the focal length and all of the camera constants of the satellite in order to then place the planetary objects exactly on a simulated pixel and line space of your camera. And from there, it pops out a picture of what you need. So what we want to do is then get an algorithm that'll be used for real spacecraft. So we cannot use the previous algorithm in deep space because we cannot obtain a position difference from the satellite to the planets just using optical measurements. So we want to take the derivative of that with respect to time, and we get the algorithm that you see on your screen. This allows us to actually use data that we can obtain from a star tracker, and that is the difference in position of the spacecraft relative to the planetary bodies, or the velocity between the two of them. And we can do this by taking pictures over time and then combining that and filtering it and iterating on it. So how the software is structured to flow is we have the picture times and the camera pointing that create your scheduled picture sequence file. This is then run through the trajectory geometry program, as well as a star catalog and ephemeris file. You get a predicted picture sequence file that is then run through OOPG to get your partials and your observations. This obtains an optical regress file that is then run through ODAP to get your final solution out. How we have modified that is by adding in a time modification of your scheduled, of your picture sequence file before it is run through OOPG. We then put a guess state into the OOPG program, and this is what I'll get into later about how we set up the simulation. And we have a truth state that is run through the trajectory geometry program. So the pictures that are predicted and simulated are the truth, but the satellite doesn't know that. So it has a guess state that it is actually running through the partials and the filtering. So to create a realistic scenario for a spacecraft would experience on orbit, we needed to create something that would be able to iterate on the solution. So to iterate on that, the time and state vectors output by ODAP are then fed into the picture sequence file again, the same picture sequence file, so we haven't changed it. We're just iterating on the pictures we already had. And then that is also put into OOPG. And that is rerun through OOPG and ODAP to obtain a new solution. This is then continued until convergence occurs. So you can see here that the new estimated time gets put into the modified picture sequence file, and the new estimated state gets put into OOPG. And so those two pieces of data are the solution space that comes from ODAP. So for results, if you have a known trajectory from your last state, meaning that part of your saved files isn't corrupt or lost, you can then use that to obtain an along track position and velocity based on your updated time. So if you have your time solution in this instance, it can also equal a position and velocity solution, but you have to have a previous saved state on your spacecraft. Otherwise, you're going to go into an unknown previous state, which is known as the full lost in space solution. So what you have to do for that is obtain an initial guess. You're basically zeros across the board for your time, position, and velocity. So you have to do something that can create an initial guess. This is where that irradiance measure comes into play. For this, the Marco satellites, what we did is we just added a percentage of how off the radiance measurement would be. So our truth is 587, and we said that we had an initial guess of 603. We also varied the angle in order to get a time update based on like the relative locations of the planetary bodies you're observing. And we fed that through as well. So we were 1 degree off, and this is unrealistic for a fine sun sensor. We wanted to make sure that we were robust to different errors. From there, you calculate a new position based off of the angle and the irradiance measurement. And then we also, based on that angle off, we put the time as 1 week off. So the spacecraft has been down for 1 week. We also simulated noise and a half pixel error for a more realistic simulation of what you would see on orbit. So what we end up with is a truth state on the left-hand side and an initial guess on the right-hand side. As you can see, the velocity components are set to 0, and they are not part of the initial guess. This is by design, as in order to obtain a velocity guess, you need to iterate on the problem, and the data used for the guess is just a quick snapshot. So we just take it once, we get the truth state, or we get the initial guess state for the position and the time, and then we move on to doing the actual simulation. So for the picture sequence that we are taking, we take 180 images of the Jovian system or Jupiter in the first minute, and then we wait a minute to simulate slewing, and then we take a picture sequence of Saturn, do the same thing for Mars another minute later. And this is done every hour for 12 hours. So you have a 12-hour total picture sequence that only takes pictures at the top of the hour. Now the results of this was run for a December 2019 sim. This was a year ago, obviously, or 6 months ago. And so we haven't heard anything from Marco, so they're not going to come up in December of 2019. So this shows all the iterations that were done. The first runs were only done using planetary bodies, and once a sufficient threshold was met, the Galilean moons were added. Convergence was determined when time was less than the uncertainty, and then that's when the Galilean moons were added onto iterations 5 and 6. The final time error that we received was less than 60 seconds once the moons were added. And so for that, here's again the truth state and the initial guess. And then this is the final state that was obtained by the simulation. As you can see here, the differences are all less than 1,000 kilometers. And the velocity difference for all components was under 21 meters per second, and time was under 11 seconds. So there are some non-linearities present that exist here. This can be lessened by taking a longer picture sequence or having better optics or taking more pictures. And so with that, you can have the Marco satellite recommunicate with Earth because it now has its position and time. So in summary, the lost in space problem, time, position, velocity has been solved. Within a short 12-hour picture sequence, time was obtained down to 11 seconds. This will be implemented on future NASA missions going out to Europa and Enceladus. And because a small sat framework was initially used, the solution is instantly applicable to larger spacecraft. If you have any questions, please feel free to email me, and I look forward to having conversations about this. Stay safe and stay healthy.